So it's about 4:12 now. We're going to get started. Sorry, 2:12, just testing you. And that previous slide you just saw was my other talk I'm doing tomorrow on Apache Spark. So today we are going to talk about Java and the GPU. And it's going to be all you need to know to get started for yourself. There's a hell of a lot of code. It's going to be quite a technical talk. I work at IBM Hursley, which is a research and development lab in the UK. And basically, I've been given the task for the past 4 years to go and try new things from Java, see if it'll break, see if it's production ready, test it out, and show it off to people. I'm going to tell you about these things, the good and the bad. So who has used a GPU from Java before? Raise your hand. Anybody brave enough? So maybe 2 people. Who's used a GPU in general? Put your hands up. So who's played video games on PC, PS2, Xbox? Chances are using a GPU. I'm going to tell you about a few interesting projects as well, like TensorFlow, Deep and show you a few Java APIs as well. Again, there's plenty of code to show you. This is the usual safe harbor bit. That's on screen for like maybe 1 or 2 seconds. Fits on the video. Same story here. I use a bunch of trademarks for different projects. By the way, there's no liability except if I'm about to show you. So I used a laptop that's not this laptop. My laptop no longer has HDMI support enabled. I had to go into the BIOS and change a few things, and I was doing some pretty dangerous stuff with the GPU. So no liability, please don't break your own work laptop. I've done some experiments to show you with lots and lots of threads from Java, just so you can see what happens. Spoiler alert, it'll all crash and burn. Messing around with graphics drivers on your only work laptop is a terrible idea, because you won't be able to get the X11 stuff working ever again, and you've got to reinstall the whole thing, and it's a pain in the ass. What I won't cover is a very in-depth look at the alternatives, of which there are many. There's some really good projects out there, like Apache, TensorFlow. I'll tell you what those are, how you can get started, but those are really worthy of their own talk. They're that interesting. Debugging and profiling. You're going to be in the CUDA world, which means anything goes, so you can get seg faults for plenty. You'll be getting GDB out and getting stuck in with low-level debugging. Impressive applications. It's going to be a GPU-type presentation, but I'm just going to show you some code, really. If you want a real impressive application for using GPUs, there's a project by something called CJ Johnson, and he's actually using Torch with Lua and GPUs, and he's applying this fast-forward model to pictures on the webcam in real time. So you see my face, and then you'll apply a filter to it in real time. Use a CPU, instead of it being about, let's say, 30 frames per second when you're playing Call of Duty, let's say, it's more like 30 seconds per frame on the CPU. It's that slow. You flick a switch on the GPU, everything's smooth and nice. So how popular is Java? There's been a few talks today about Java, and these are the projects that I'm really interested in. In IBM, it's on our mainframes everywhere. Some analytics offerings are using it as well. Apache Spark using Java, and all those other cool Apache projects. So it makes sense to try to use these GPUs I'm going to tell you about from the Java world. Now, what if we tried to do lots of things at once in the Java world only? There's a Stack Overflow post I put at the bottom here. You basically have a custom thread pool, and you will see how many threads you want to try and run at once. And you can play around with this and see how many threads your machine can handle. So you can ignore the DevOps bit here. This is from a previous presentation. But I just basically built the application on the previous slide that uses the set property for the number of threads I want to run in a thread pool. And here's just, ignore the 50 elements, 50. I want to just run 8 threads in Java. That's all fine. Everyone's happy. About 10 seconds to finish. No issues there. We then do 50 threads. OK, it's fine. Finished instantly. No issues there. We then number of elements, 50 as well, no issues. This is all fine. More elements to process, less threads, you're still fine. Then you go to 1,000, and still fine. Laptop's a bit noisy, so the fans are all going full blast. Then you try to do 50,000 threads, and this is where the bad stuff happens. So CPU and fan, really, really loud. No memory to get any more new threads, so I was basically looking at my laptop and it was trying to take off and I was getting upset. I can't terminate the process in my shell anymore. I was pressing Control-C and that does nothing. I can't get another shell up to a kill -9. No memory to create new threads. Mouse was stuttering about and I'm there struggling. JVM, so IBM JVM likes to try and create core dumps to help you to debug problems. The only thing is, that's going to need some memory to create those. And I've got no memory left, so just all dying all over the place. LibreOffice crashes. I was trying to screenshot this all for you. I couldn't, I pressed print screen, nothing happened. LibreOffice was dead. Select out Control-C, no new processes. Watched to get a print screen, nothing happened, rebooted, and I cried. So that's when you try to use loads and loads and loads of threads in Java. Terrible idea. What you can do instead is try to reach out to the GPU for more processing power from Java. And the use cases have all got the same sort of thing in common. You want to achieve your results fast. Remember what I mentioned earlier with that fast-forward processing, where you apply an effect to a few images. I don't want 30 seconds per frame. I want it the other way around, basically. I want it to be fast, 30 frames per second. Typically, you want to send down a lot of data at once. So in an ideal world, this is in deep learning for J, you actually try to keep the GPU busy as much as you can using CUDA memcopy async. I'll talk about it later. You just send data to the GPU, do some work, get the result back, keep going. You don't want to do this. All right, GPU, I've got some work for you. It's got to be really big. You send down 8 gigabytes of data, and then you wait about 5 minutes, and you get a result back, and you say, yeah, that's a nice picture of a penguin. That's terrible. You want it to be real time, send data to the GPU, get back what you can, and keep going. Again, it's great for machine learning. So alternating least squares, logistic regression, naive Bayes, k-means, all really good for the GPU. Neural networks as well. So who's actually using GPUs already? Recent press announcements. AlphaGo, be a Go champion. Again, using a lot of CPUs and a lot of GPUs. You have them in data centers appearing. So for example, there's the Oak Ridge supercomputer, the Titan supercomputer, all have lots and lots of GPUs in there to do really hard processing. And here you can see there's a recent Amazon announcement. You can get GPUs on AWS. And even more recent, I think it was in the past week, there was the NVIDIA announcement, the NVIDIA cloud. Here's a depressing story for you. Started working on GPUs about 4 years ago. NVIDIA share price was about $13 per share. Within the past week, it's now about $130 per share. If I believe my own hype, I might have invested in GPUs and made a good return, but I didn't. So GPUs are really taking off now, and I guess going to be in a lot of data centers near you. I always get this NVIDIA email. It's like every week, and they say, oh, all these cool things happening with GPUs. Okay. I go, okay, fine, I'll click on one this time. What cool stuff are you doing now? Well, deep learning to combat asteroids, so can you detect if an asteroid is going to approach or not? What you do afterwards, once you know it's coming, is another matter. I don't know. Detecting the road lanes of deep learning, so you want to drive down a lane, you want to figure out if there's a dog in front of you. I don't want to wait 30 seconds to know that there was a dog in front of me, but I've just run over it. So you want real-time things. GPUs are good for that. Identifying skin cancer, lip reading AI. Again, if you get the lip reading wrong, you've got to wait 30 seconds. You're never going to use that app ever again. It'll be terrible. And life-changing wearables for the blind, so you can actually get a phone and just hover it over some images, and it will read out what the thing actually is. Again, 30-second example. Identify this water for me. I hold my phone over it. How do I even know there's water there? Feels a bit like water. Can I wait 30 seconds? I've moved on. I'm impatient. So GPUs are good for that sort of thing. So they're good for doing many of the same operations at once. There's a single instruction, multiple data programming. And the analogy that I always use here is on the bottom. GPU, these little ants doing lots of the same simple task at the same time. CPU, more like a dung beetle, so pretty strong, pretty big, pretty powerful. You need pretty complicated things, but you can't really launch 50,000 threads. Not in the same JVM, at least on the same machine easily. So that's the analogy I use. And you can get these CUDA drivers for a bunch of different platforms, so Windows, Linux, and IBM systems as well. We're going to use CUDA or OpenCL. All the examples here are in CUDA. If you know C and C++, you're going to like CUDA. It's very similar, but you get some special functions to use GPUs explicitly. And then what type of GPUs can I get, and does it even matter? So there are your normal graphics adapters that you might plug a monitor into, typically about 2.2 to 4 gigabytes of memory, less than 1,000 processing cores, and each of these cores might have a pretty low clock speed, so about 1250 megahertz, let's say, and you're going to find these in your laptops, in your gaming computers, perhaps. The experiments that I used, that I'm going to show you at least, run that specification there. So it's pretty good CPU, CUDA 7.5 and MEL 7.3 with 32 gigabytes of RAM. You also get these high-performance cards, like the Tesla series. And again, there's going to have way more memory in this case, so 8 to 24 gigabytes. Thousands of these little processing cores to use. And if you want to measure the performance, it'll be in teraflops. So maximum memory bandwidth, pretty good. The only thing is you might need your own cooling system, physical security. You've got to get a GPU like, let's say, a K40 or a K80, probably about $6,000. So it's going to be quite a lot compared to the little ones in your laptop. And again, the thermal design power rating on these is going to be a heck of a lot more. So you need a lot of juice to power these GPUs. If you actually get the CUDA toolkit, which is free, you can do this device create program. That will tell you what you have on your laptop. So again, it's sort of a piddly GPU, not that good. These are the specs here, so not many cores. Those that really can't read it, 512 CUDA cores, about 2 gigabytes of memory. It's not that much. I can still use it though, to do some pretty cool things. There's a bandwidth test as well. So getting memory out from the CPU, normal RAM, conventional RAM, is going to take a long time typically. So you can actually run a bandwidth test to say how much I can get down to the GPU. And if it's going to take you forever, then I won't even bother with that application. So this is all for free. Here's my information for the CPU and RAM. Basically, it's a lot of cores and a lot of RAM. It's pretty good. So what's the GPU good at then? I told you about machine learning. Your data needs to be in this kind of format. Primitives, GPU's got a fetish for primitive types. Ints, longs, shorts, floats, that sort of thing, really good at. If you want to get complicated and use things like files or doing networking, stay away from using GPUs for that. This is your core logic, your big for each loop that's taking you forever to run. Here's where you'd use a GPU. So matrix multiplication. So in machine learning, you do a lot of this. It's really fast at that. Simple transforms. I've got 1 billion records. I need to add 10 to all of them. GPU is going to be fast at that. Finding a pattern in your data. So you could download Wikipedia dump files and get lots and lots of them, those files, and look for certain words in there. So maybe do a word count on Queen or GeeCON or Poland, whatever. If it's a lot of data, you've got a good chance of getting the speed up on a GPU. When I say speed up, this isn't like 10%, this is more like 10x for the right sort of problems, even 100x. Your operations have to be quite simple though. So arithmetic operations, really good. Networking, no, don't bother. So again, not so good when the data isn't self-contained as well. I want to get data from this data source, put it onto a GPU, but I might need data from over here as well. It gets a bit complicated. You want to do it with really simple operations, non-blocking ones, keep it nice and simple for GPU. So how might we use a GPU? There is a really, really horrible way to do it, which will give you some nightmares, and then we go on to the easy stuff for everybody. Horrible stuff is basically that. So you declare a normal C-style integer array, you do a CUDA malloc call, you do a CUDA memcopy, then you write this GPU function, get it all back. Doesn't sound so bad so far, but you can do it a lot easier than that. Here's how you write a GPU function, by the way. That's called a kernel. And essentially, that __global __ this is a function you can call from the CPU. So from your normal Java program, going out to the GPU, let's say, and here we're just going to have integer start array 1 and array 2, and we're just going to do some simple maths here. So that is how small your GPU function might be. And I would say in an ideal world, it gets to maybe 10 times the size of that, so about 10 lines, and you're fine. Don't go writing your entire web server in a CUDA kernel. It's a terrible idea. So that's what a global function is. How's the data actually arranged? So I've got all these different threads. I've got 10,000 threads, 100,000 threads running at once. How do you actually coordinate those threads and say, you operate on this part of the array? You use built-in functions for that. So there's this thread idx.x variable. There's also thread idx.y and .z. Keep it simple. Just think of it as a big 1D array or a 2D array for now. You can control the threads using this built-in variable. And how is data actually arranged? It's got to be sequentially arranged. So that means you send down 1,000 elements, structure them all in a sequential fashion. So you don't need to random access. It's really fast, basically, on the GPU. Multiprocessors, you don't really need to know about this, but behind the scenes, the GPU's got these multiprocessors, and the CUDA cores do all the work. So multiprocessors have CUDA cores. This is all at hardware level and do the work for you. A kernel we talked about just then, a function on the GPU you can run. How many threads can actually run at once? It's going to be in the millions, hundreds of thousands, millions, that sort of number. So a lot more than on my laptop where it died at 50,000. At 10,000 it would have died as well, I'm sure. So how much do I need to know? A little bit here about the grid. I would say we're going to skip this for now for time. But you can use this one command called NVIDIA-SMI. That just tells you a simple way of telling you how much memory you've got on the cores as well. A bit like device query. But you might run a program. How do I know if it's going to the GPU or not? You'd run NVIDIA-SMI in the background and you'd see it. And that's all for free with the CUDA toolkit. I'm going to skip this slide. It's to see how many blocks and threads you need to run a kernel. Here's the CUDA code. This is the hard way to do it still, by the way. We don't want to do it this way. You basically have to do your malloc, let's say, integer array. You're going to fill that array up, normal C programming. Then do a CUDA malloc. You see it, let's say, up here, CUDA malloc, CUDA memcopy, then call the kernel. So what I mentioned earlier about the different arrows, this is our kernel. I'm calling the kernel with this. Number of threads I want, 256. Number of blocks I want, let's say that's 1. So this will be 256 threads, and we're going to do it on how many integers in this example? 5. But I want 256 threads, let's say. So this is quite dangerous in the example here, because you will go out of bounds and run over it and either get junk data back or a seg fault if you're particularly lucky. So this is all in the unsafe world, remember? Vanilla Java, this is where it gets even worse. I'm going to make it easier on you in a few minutes' time. This is in normal Java, integer array. You want to do the same thing. You've got to basically go through JNI, so you write your own C++ code, then go down to CUDA, do all that fun stuff I've just shown you, and then go back to JNI, then go back to Java. So this is going to be error-prone, complete pain in the bum. This is horrible stuff. Working example with that, you need all these files. So NVCC command, that's sounded like the NVIDIA kind of compiler. Think of it as a compiler for now. And then Java code, header file, C++ code, CUDA code. And then all you get at the end of it is that. So yeah, I just added 10 to some elements. Not really interesting at this stage. Pitfalls to look out for, loads can go wrong with that. Use objdump, use that command. Look for things like name mangling of symbols, world of pain. Segmentation faults everywhere, world of pain. Don't do it that way. Printf statements are going to be your new best friend. Those Java debugging things you really like to use, like, I don't know, maybe mission control, maybe health center, different monitoring tools. Nah, they'll be useless for this. So check your memory accesses, don't go out of bounds, don't do it that way. Simple way, yes, sticking to Java as much as possible because we like Java. For a few reasons. There are lots of cool projects in Java. Once you use GPUs from them, okay, now you can. We get error checking, we get type safety. Some nice debugging tools are out there, profiling tools. We get nice JIT compiler, garbage collection, all that good stuff. And kind of portability, if there's a JVM there. I work on Apache Spark for my day job now, and there's a lot of some risk on safe usage, breaks on big endians, some mainframes. It's kind of portable. We make it a lot easier for you to do that. to use GPUs. We're going to change a few things. The Java class library itself that you get for free, so what's in rt.jar, the JIT compiler, and give you an API to use as well. And also change Apache Spark to use GPUs behind the scenes. Here's the Java class library example. So it's not very exciting at this stage, more of an experiment. I want to sort a lot of integers. I really like sorting integers, let's say. Fantastic. What you can do is use a GPU with one option. You just put that up there, -d com dot blah, 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 and essentially you will get a performance boost if you have a GPU. Behind the scenes, what we're going to do for you is see if your problem is big enough. If you've got 10 numbers to sort, you're going to be using a CPU, unless you put the override on called enforce. You got 1 million, go on then, use a GPU and it'll be faster for you. We'll check if there's a GPU available as well, and if it's actually capable. You might have some archaic 10-year-old Sapphire 32 meg GPU. It's got no CUDA support at all. You're not even going to try to use that. That's one way to do it. The second way is by changing the JIT compiler itself. So you might be able to write a for loop or a double for loop, maybe using this int stream class in Java 8. We can look at your code and say, you know what? It looks like I can offload that to a GPU. You've got this int stream going on between a certain boundary, so from the start of the stream to the end of the stream. I'm going to generate some code for you, run it on the GPU, and it should go faster. Again, Java options for it for you, the -xjit enable GPU option, which is all given to you for free in our JDK, which will be open source towards the end of this year, by the way. Results on my laptop, you can see here. So we've got a 42 seconds to basically multiply this matrix of 2048 elements together, about 40 seconds, not very good. GPU, more like 1 second, and what did I do to enable that? All I did was that, basically. -xjit enable GPU, and we handle all the hard stuff for you. We generate the PTX code and do the error checking and exception handling and send it down to the GPU. That's another way to get speed up. GPU lambdas, different benchmarks. Not really a big benchmark fan, more of a micro-experiment fan. I can show you things as I go. But this was formed in a Tokyo Research Lab. And apparently, with 160 CPU threads versus a GPU, performance, it was a good GPU, mind you, kind of looks like this. So in some cases, it's around 50x, 60x, 100x, 260x, heck of a lot faster than using one CPU thread. And against loads of CPU threads like 160, about 4.7 to 14 times faster. For some benchmarks, not so fast. So again, it depends really on your workload. And if you're really serious, you'll be benchmarking as you go anyway. Again, the benchmarks we used that was told you about are described here. So it's some sparse matrix multiplication, Jacobi 2D, and Conway's Game of Life. I encourage you to try this out for yourself and just any problems, you can email me directly. You'll get it at the end of this presentation, and I can look into it. Some advantages. Why would we want to do it this way? We want to make it really easy for you guys first. So you just run a program. It's faster. Great. Standard Java idioms. So you're not learning a new API from scratch. Normal Java semantics will then apply. You don't need to know about GPU programming, just use an option. All of the details are done for you. This will actually choose the optimum mode to run it in as well. So CPU, GPU, or auto SIMD. And then there are future improvements we might make, where all you have to do is run your program with this option, and oh look, a month later you run it again, and it's just gotten a heck of a lot faster because they've changed the JDK itself. So the JIT will take care of the data alignment as well, to properly use like the L2 and L3 caches, do all this for you, and the data transfer. Remember what I mentioned earlier about using, making sure the GPU is busy all the time? We'll handle all of that behind the scenes in the JIT. There are some limitations, mind you. The GPU memory is not an extension of the Java heap, not the same thing. You still have to get your data out of the normal Java world, your Java heap, to the GPU. Which might take a while. So if it's 10 elements, remember what I said earlier, don't bother using a GPU. If it's more like a gigabyte, we can use a GPU. So heuristics in there. So we've actually benchmarked this, what I mentioned earlier. So we'll say, looks big enough, looks okay, off the GPU you go. You can override these as well if you wanted to. So you can always use GPU lambdas for verbose to see what's going on, or enforce. Remember, this will all be open source anyway down the line. So if you want to improve on it, you can do. You find a nice bug, you can raise an issue, do a pull request, that sort of thing. There's also a CUDA4J API as well. So there's something called JCUDA, CUDA4J, not the same thing, but kind of similar. JCUDA is more like, I really know what I'm doing with GPUs already, and I just want to access things as pointers. So it's going to use longs everywhere to store addresses and then access things via that address. CUDA4J is kind of a more Java-friendly approach to doing GPU programming. You still need to write the hard part, by the way, which is the kernel that I showed you earlier. Again, that should be really, really simple, like 1 line to 10 lines, no complicated code in there. But the Java bit you can actually just do with CUDA4J. You do a few imports, so com.ibm.cuda and CUDA kernel, and then once you've compiled your kernel, the .cu file, you will then load that module, and you can access it then from the Java normal world. That means there's no need to write any JNI code. You have to load the library, for example. It's all done behind the scenes for you. So there are a few things here of CUDA that you should know about as well. You might have 10 different GPUs. So we would have a CUDA device, Java object, that would be used to reference a certain GPU. So you could say, well, GPU 2 is really, really fast. The other ones, not so much. So you could change your code to say new CUDA device and then an index to point to that GPU, and then make sure your code always goes to the fast GPU, not the slow ones. The alternative would be that you either go into your settings and disable that GPU with software, or you just take the back of your computer off and pull out the GPU. So these will all map on the left, these classes, to those different things on the GPU. Here, I'm only doubling integers. The idea of this talk is to really give you inspiration. So I'm going to tell you what you can do, and then you can go away for yourself and give it a try. That's what the code looks like on the left that's all Java. So I'm just loading up that module, the kernel, and the kernel itself, if you can see at the bottom right, is only a few lines of code. And all I'm doing in this case is just doubling some integers. So basically, I would compile that code with the nvcc command, load that module from Java, and then use it. And this isn't much code at all. Earlier, it was like 5 pages, not 6 pages, of writing C++ code, writing loads of CUDA code, writing loads of Java code. Where would it actually be useful then? So maybe it's in your existing Java programs you want to start using a GPU for. If it is this case, please, please, please do the profiling first. It should be a no-brainer. Mission Control or Health Center or tprof, jprof, these sort of things. Maybe just print lines everywhere. Make sure it's a lot of data you can actually use, and then start thinking about using CUDA4J, let's say, or maybe JCUDA or TensorFlow. Don't do it for your simple 10 elements. Change the heuristics as you see fit. Do a lot of benchmarking all the time. So if it uses the GPU or not, there are trace options you can use. I just recommend NVIDIA-SMI, because that will say, I've got this Java process using 10 gigabytes of memory, and then chances are that is actually your Java program, hopefully, not some random person's using the GPU. There are some big GPU limits, mind you. They're not going to have much memory. There was a recent Amazon announcement, I think it was 16 terabytes on some of their servers in the cloud. Well, remember what I said earlier about GPUs, the really good ones are about 20 gigabytes, 24 gigabytes of memory. So what you might actually do is chunk up your big problem into smaller ones and do a little bit at a time, get the result back a little bit at a time. That's only going to make real sense if you get a big speed up for those little problems. Because remember, you've got to copy it over the bus to the GPU and back again. But what we can also do is improve other projects. So Apache Spark, let's say, maybe you want to do it to Hadoop MapReduce, maybe you want to do it for Flink or Kafka. We've done it for Apache Spark itself, which is, so first of all, we'll have a drink. Who actually uses Apache Spark already? Can we put your hands up? So about 10 people, okay? So for those that don't know Apache Spark already, Really, really popular open source project for machine learning and graph processing, streaming of data. You can use different input formats. So let's say it's some HDFS. I want to read in Parquet files or JSON files. I can use Python with it, SQL-like commands. And what we're doing in IBM is saying, you could all go away and write your own analytics programs and maintain it yourself, or you could all use Apache Spark, and we'll improve Spark, make sure it works, and everyone gets a knock-on benefit from doing that. That's the approach we're taking. So if you make Spark faster, make it faster for the community out there using it and testing it, anybody else, and also ourselves as a company. So you can change Spark to use GPUs, as we've done, and also Deep Learning for J have done with great success. You can use it with things like Kafka and Hive and different other projects. You also get some nice benefits, so auto compression, fast serialization, and it'll scale out as well. So it's pretty fast. This is where your problem isn't the easiest thing to do in parallel. So maybe it's some quite complicated code. You might use Spark to scale out. If it's quite easy to write the code for, you use a GPU to scale out. How do we actually do this? Alternating least squares. So I was explaining it the exact same way. It's maybe I like these 3 different movies. It's Jumanji, Mortal Kombat, Blade, let's say, and then somebody else likes those 3 exact same movies, and they also like The Lord of the Rings: The Two Towers, and then you'll be able to infer that because Adam likes these 3 movies, Billy Bob likes these 3 movies and Lord of the Rings. They're kind of similar movies, so Adam probably likes Lord of the Rings as well. So this is probably going to be how Netflix works, recommendations, maybe Spotify for songs, YouTube recommended videos. I like these 5 videos, so does this guy that's like me. I probably like his videos as well. GPUs can be used to speed up that the algorithm by about 2 to 3x using GPUs versus Spark. Clustering. So K-means clustering is quite popular. You could use GPUs in this case. Identifying anomalies might be a use case for doing that. And then classification algorithms. So maybe you want to build a spam filter. You want to do some, there's a really good banking example where you basically get loads and loads of different investments being made, and then you've got the scores for how good that business is at certain things. So for example, if it keeps failing at, I don't know, the amount of debt it has, you can infer quite easily that it's going to not be a good investment. So you can handle these sorts of files like a CSV file with banking information in and come up with a model. And if you got some new data coming in, this dodgy business keeps failing all of its stress tests, loads and loads of debt, the GPU, this algorithm will just say, yeah, don't bother. It's a yes or no answer. Yes, invest, or no, don't invest. So Spark's good at these, and therefore, in theory, so is a GPU. I've already told you how ALS works, so I won't repeat myself. Basically, a cool band, 1, 2, 3. You get the idea. So you can infer things. We've actually got a full paper on how we actually did this. It was in the Watson lab in the US. And then those guys said to me, Adam, we've got this really cool solution here, but it's from IBM research. We're not sure if it's production ready yet. And you're making this Spark kit. So can you give it a go and test it and ship it? I said, yeah, go on then. Got the hardware, did the testing, and then we released it with our Spark package. And you can see here on this Netflix data set, about 1.5 gigabytes, that we got a decent speed up versus the CPU. So about, let's say, 3x using the GPUs in this case. The thing is, these were quite powerful GPUs, the Tesla K80s. So if you were to do a price analysis, you're probably still a lot better throwing CPUs at the problem. This is only really going to be good if you want an instant result. If you go onto Netflix now, and I want to get, let's say, a recommendation, and it's got to take me a minute, I've already gone, I've just used another service, I'll never use you again, I'm going to boycott you completely. It'd be so bad. So you want real-time results, so you would use a GPU in this case. And how do we actually do that? We did this in parallel, and the whole theme of this talk is doing things at the same time. The really old, horrible, busted way, because we want to make it work with OpenJDK as well. Now, at the time we made the Creative4J API, there was zero plans to open source the IBM J9 VM, which basically meant that we did it this terrible, terrible, terrible way. So hopefully things will all change when we open source the VM, and we'll do it the nice way. But until that happens, you get this old, busted way of doing it. But it does actually work. You can get the Spark package, you can specify an option, and onto the GPU it would go. And then please don't raise a bug against it, because I've got to go into that horrible, horrible C++ code and that CUDA code. So if you want to raise a bug against it, you can wait until it's all refactored. That would be really, really good. So you get a shared library with it. If you don't have the shared library, it's not going to work, because it's all native code, remember? And it's just libgpu_als.so. That diagram there is one of the most common Spark diagrams out there. The main message it tries to say is you've got one little workload in your normal program running with a Spark context object. It talks to a cluster manager. Let's say it's just a normal Spark master, or with Yarn or Mythos, let's say. And then this will spawn different executors on different machines that will actually do the work for you. These executors can basically grow some intelligence and say, have I got a GPU or not? Well, I do, so I may as well use it. And then it will process your data quicker and return it back. One massive, massive, massive issue with all of this, though. What if all your executors don't have GPUs in the first place? And the other issue is, if one GPU is so much faster, shouldn't we change the scheduler algorithm to say, instead of using 20 CPUs, when 19 of those CPUs, let's say, will take forever, but your GPU is already done, and it's just sitting around waiting, it's not going to work, because you've still got to wait on the CPUs to do their thing. So what you really need is an all-GPU cluster, and that would really be the end game, which is a bit annoying and really expensive as well. So what we can also do is change the data frame API. Now, a data frame API is where you do an SQL statement on loads and loads and loads and loads of records, let's say. So you've got this really big monolithic table. It was built about 10 years ago. It's got, let's say, 500 billion records in, and you just want to do the same operation to all of those. You're going to write your normal Spark code, some SQL functions, and like I told you about the lambdas earlier, we'll look at the way you've written your code and say, well, you know what? GPUs are good for you as well, and then send it down to the GPU and get the results. What I've got to do to this is to change basically the catalyst optimizer. So in Spark, it will try to rearrange your SQL queries to make things quicker. Spark also uses Tungsten, and the idea behind this Tungsten project was to bring Spark closer to the bare metal. So it brought it pretty close by basically using some misgun safe everywhere, so break things for us. But it made things quite a lot faster for OpenJDK users and Intel users. We want to bring it even closer to the metal, but now you're kind of thinking, why not just rewrite all of Spark in C++, or just use CUDA? Well, you've got a heck of a lot of Scala code already, and you want to use it with Java projects out there, things like Hadoop or Hive and Kafka and Flume, whatever. So you're going to write it all in C++, but how do you use those? Do you use JNI, then call Java from that? Because we're all on the Java bandwagon already, it makes sense to do it the opposite way around, which is where you add the GPU support in to those Java libraries as it is. If you add it from scratch and all the other projects are in C++, maybe it's a good idea. The output, when you actually write your code, needs to be like this. So when you're thinking about writing your analytics going forward, if you keep this in mind, you might have a nice Christmas present for you, which is basically, we've seen your code and optimized it for you. But it has to abide by these rules. So the data needs to act in a linear fashion, a counted loop, not many branches, so it's quite simple code. And then we're going to write a good JIT compiler that will optimize that for you. Lots of different issues with this. Long story short is there are these 4 main problems in Spark itself. And we have to change the Spark code itself and push these upstream. What you get from that is these kind of numbers just with the CPU so far. So these were merged into the Spark stream in the community. And you're already seeing some, let's say, 20%, 70% okay improvements, nothing that impressive on their micro benchmarks. So we want to finish it off and give you the present, which is the GPU offloading capabilities. Again, some more things here. Here's a nice 16.6x eliminate boxing. It's okay, but bear in mind it's part of a micro benchmark. So you might have a really big program that takes 10 hours to run, and maybe we just made 0.2% of your program run 16.6x faster. So that's not very good in itself. It's the bigger picture that you need to care about, hence why you need to profile it and then optimize those functions. If you're at a boxing benchmark, like that probably is, by the way, yeah, you get 16x on a CPU. Not that good. It needs to be the whole picture that we optimize. So what's in it for you? We want you to be able to build our GPU applications easily. We can figure out the hard stuff if you don't want to using the JIT compiler, or you can use CUDA4J, for example. You want to stay in the Java world. This is welcome to the JVM world at the top there. So we do like Java. We want to stay in Java. And like the Oracle chap earlier said, people keep saying it's going to die soon. Is it dead already? Well, it's not really, is it? Look at the number of Apache projects out there and how much Java code there is and legacy applications. It's not going away. And again, people are trying to use, let's say, JavaScript at university. Well, what about all your different types? You're just going to say the compiler for you. It'll be around for ages in Java. I'm sure about that. So ongoing work that you could probably apply to different projects. Some big challenges, by the way. PCI speed, your PCI Express bus, might be the world's fastest GPU. So you've got to get your data onto a GPU in the first place. That's a big limitation. If you're a big company of like billions and billions and billions spent on research, you can make a faster PCI bus. So we did that on Power with NVLink. And you get decent speed ups because it's basically sharing the same interconnect. Yeah, I wouldn't bother if you're just a normal developer though. Writing a kernel, that's the really hard part. So I met with the DeepLearning4J co-founder at San Jose in DevOps, and he's telling me how DeepLearning4J is used in a variety of big companies. It's basically GPU-enabled machine learning for Spark, so neural networks, AI stuff, machine learning, really cool. And he says, of all the employees they have, I won't tell the exact number, very, very small fraction know how to write the kernels themselves. And I bet you, if you know how to write a really good kernel, you can probably demand a lot of money in wherever you go to work. So writing the kernel is the hard part. The Java part should be the easy part. Same for C++ as well. Again, not many GPU developers are actually out there. So it's getting quite popular now with the NVIDIA cloud, let's say in AWS, but there aren't really that many people doing it. So obviously go to the NVIDIA forums, ask us questions, and we can go from there. YouTube, I would say, really good resource. Just go on YouTube, like every video there is out there to have GPUs, and watch those and see what you can do for yourself. The CUDA SDK, remember this is free. There are some changes that were made in the past few years that are really quite good. So pinned memory and reducing the need to transfer data from the host to the GPU over time. So make sure you're using the latest CUDA toolkit if you go down this path. And profiling, by the way, you could spend your entire life profiling this kernel to really, really, really good. Different things to tweak, more pitfalls than Java, unless you're going to be naughty and use Sun Misc unsafe. By the way, who else is using Sun Misc unsafe here? Anybody else using it in production? Okay, I'm the other person. Okay, good. Excellent. So CUDA itself is a pain to set up on my laptop. I'm sure it'll be easier if you're on a machine without a actual display, like a server. But because it was my only way to do any work, it was a big pain to set up. Basically, it's an Optimus one. I had to go into the BIOS and change it to discrete mode. If anyone has the same problem, BIOS discrete mode is good. Hybrid, and we get a terrible error to with the desktop. Debugging, really, really hard if it's got a million threads running at once. And what you really want to do is focus on that kernel I told you about earlier. What else could go wrong? Bad JNI code. This is the hard way again. You write bad JNI code, you write bad Java code, bad CUDA code, bad C and C++ code. That's a presentation, that's a book in it, that's like 10 books in its own right. What else could go wrong with this, unless you do it the way that we're kind of preaching to go down the CUDA4J API route or the library route. Bad design, you just chose something that's not good for the GPU. It's way too small. It's like 10 numbers. Again, don't bother. Can also be too complex. You keep using like the network for some reason, using some really weird if statements everywhere and some nested loops and all that don't bother on the GPU. Way too much data. I've got 10 terabytes to process, so I want to do it all in one go. Can I use a GPU for it? Maybe if you're alive in 500 years' time, and GPUs are still a thing, sure, but now, not much memory to go with. CPUs are already good and pretty cheap anyway. You can probably get 32 CPUs for the same price as one good GPU. Use Spark instead. So I realized at this point that I may have just completely undersold what I'm talking to you about GPUs. But they are good for real-time things. Profiling, make sure you are compute-bound, not network-bound. If you go and invest $10 million on your GPUs, but you're actually network-bound, go and use RDMA and InfiniBand instead. And then finally, in closing, well, it's actually out there. There's OpenCL, you could use instead of CUDA. I would say that a lot of the attention now is around getting things to work with CUDA, and NVIDIA market share is pretty good for GPUs. So other open source projects probably have GPU supporting CUDA, but perhaps not OpenCL just yet. TensorFlow, that's quite nice, really easy to use. Different APIs on there for machine learning. And then SystemML. Basically, you would use their own DSL to write your machine learning in. And then we would say, off to a GPU you go, or off to Spark you go, for example. And those are all free to use. JCUDA, again, what I mentioned earlier, it's kind of like you already really know what you're doing with C++ and you just want to use pointers. You can do. This is another open source project out there. There's also deep learning for J I mentioned with Adam Gibson. So this is what I'm really, really keen on now, is how to build a neural network using GPUs. And I'm sure deep learning for J can help me out there, all open source. NVIDIA libraries, so there's CUDNN and there's cuBLAST and Thrust. I'm pretty sure these aren't open source, though. These are all proprietary things. So I would say try and use deep learning for J, or use our APIs or JCUDA. And then there's this thing called Aparapi. If you go and search for AMD runtimes and GPU, at about 200 views, I think, in maybe 3 years. It's actually really, really good. And it was pure Java. You actually write your kernel in pure Java, and it looks to actually just all work nicely. So I was really impressed by that one. Again, not many people are actually watching the video at least. And then there's also Project Sumatra. So the Open JDK initiative for using GPUs from the SDK. Really good video on there. Again, not many people are actually watching it. This Sumatra Open JDK project update. So they've done a similar thing to what we did with Lambdas, using Holy Grail, I think. And yeah, not many views, but you could use it and get a speed up. So in conclusion, I would say if you want to give it a try, it's going to be free to use. You can just get an SDK for Java from DeveloperWorks. You can just get Eclipse or Spark, let's say. Give it a try if you've got a GPU. Do it on your laptop, for example. You don't need to know GPU intricacies, like CUDA itself. You just add these different options. And it's only going to be used for certain things. So don't treat it as the be-all and end-all. You're going to become a GPU master. You're going to become limited to a certain number of functions that will be faster than the GPU. There are lots of projects out there that combine the two together. Give them a try, and do look out for OpenJ9 when we open source the JDK itself, so you can have a look at the GPU implementation, raise bugs, fix them, that sort of thing. So I've got about 2 minutes to spare. Are there any questions for me? Okay, yep. Is there a microphone for this guy?
Two questions probably related. First is if GPU support is enabled in J9, will the resulting code be reoptimizable? So for example, if datasets become small, will it become SIMD instead of GPU? And the second one is all the same stuff supported in ahead-of-time compiler, not only in JIT?
So I don't know about the AOT stuff. I think we've had AOT in our JDK for a while, but not for the GPU stuff at the moment. For the first question, yes, it would be the CPU/GPU/auto SIMD implementation we go with. So for example, you don't need a GPU and we'll just optimize the code to exploit auto SIMD. Yeah, we're going to open source all of that so you can play with it. Does that answer your question? Okay, cool. Anybody else got more questions for me?
One more question here. So maybe you mentioned that, but I might have missed that. Is there a zero processor copy facility for the GPU memory, so that I tell the controller to copy from disk to the GPU and get notified when it's ready?
My guess is that NVLink probably does, the proprietary stuff. I know zero copy is really good like in RDMA, for example, so it's the same sort of thing. Not that I know of already that's available to everybody out there. There is pinned memory and host dialog functions in CUDA, where you can say reserve this region, lock it, and the GPU can just access it quickly. So perhaps in CUDA 7.5 and CUDA 8, but I've not used it myself personally. Would be really good to have though, for sure.
So the bottom line would be that if I have a lot of data on the disk and then want it in my GPU, I have to first load it into the memory and then transfer at whatever transfer rates I have between RAM and GPU, right?
So at the moment, yeah, that's what we've been doing. And that's where it can take a while, because you almost keep reading from disk all the time instead of just reading it from memory.
Okay, thank you.
Okay.